All right, team, here we are back with the 2024 derived grade exam for level 3 chemistry at TGC, and this is the Aqueous paper, and it's the last paper because last question because we didn't do solubility yet. So question 2, Aqueous, and it's the dreaded titration curve question, which many of you actually did okay. It's a bit of a horrible one, isn't it? Because it doesn't really have a great vertical section there, which is a little bit ugly, but still we can manage with that. So it is a reaction between a weak acid. How do I know that's a weak acid? Because it's got a Ka. Strong acids don't have Kas because we assume they fully dissociate, and a strong base. So the first question says, on the curve, mark the position of the equivalence point. A little bit perturbed at how many of you didn't quite get this right. Equivalence point is the midpoint of the steep section. And the buffer zone, so we're wanting the half equivalence as our great buffer, perfect buffer position, but we want to kind of go plus or minus 1 pH. That's quite a lot. So that pH there is about 9. So we can go down to, well, 8 point something. We can go up to 9 point something and down to kind of 7 point something. So either one of those for an achieved. This really tested your ability to know what was happening in the titration and not just memorize how to calculate points. So this was a worse done question actually. So what's present at the equivalence point? We had to remember that at the equivalence point, we've reacted equal amounts of these two. So we've only got products. And as you can see, they've written this together, which I don't agree with. And you know, remember that as I teach you, I always write these things in their dissociated form because they are ionic and they are in water and they will have dissociated. So you have got to remember that yourself. So at equivalence, we've just got that. So we've got some Na plus and we've got some OBr minus. But remember, this thing here is now the conjugate base of this weak acid. So it's going to react, and I might even just do this. I'd probably do this in my exam. What's it going to do? It's sitting in water, so it's going to accept a proton to make those things there. So I'd then be putting HOBr and OH minus, and I should know that there's always H3O plus. So I've kind of done that in the right order, but they didn't ask for it in the right order to be fair, but you had to get any 4 of those correct to get a little achieved there. All right, pretty standard to calculate the pH at equivalence point. So again, at equivalence point, we've only got the product. So we need to know what that product is. And because I did this equation here, this is going to help us for my pH at equivalence point. So I'm actually just going to write this here again because that's what's happening at equivalence. I have got a weak base. So I am going to do, a KB calculation. So I need to find the Kb by going 1 times 10 to the negative 14 over the Ka. That's one thing I need to do. I need to write my Kb expression. So products over reactants here. Now at equivalence point, we actually do have a pure solution, right? Because we've reacted these two in a 1-to-1 ratio and they don't exist, we've just got this. So we're actually just working out the pH of a basic salt. So it is a weak base here. This is the thing here that we need to know the concentration of. So to work that out, we need to find the number of moles at equivalence, and we need to divide that by the total volume. And that's the bit that some people forgot or couldn't quite work out. Some people didn't ice. That is actually okay, but at this point it's not necessary. And ice is necessary at random points along the curve. That makes that a bit easier. But at equivalence, we don't really need to do that. Okay, so my Kb is going to be 1 times 10 to the negative 14 divided by 2.34 times 10 to the negative 9, which is my Ka. So that's going to be 4.274 times 10 to the negative 6. My concentration here, so my number of moles, I'm just going to take my hyperbromous, so I'm going to go N equals 0.15 moles per litre times 0.0 0.025 litres, right? So that's my number of moles at equivalence point of everything, 0.025. So that's 3.75 times 10 to the minus 3 moles. Sorry, I was out of your frame there, sorry. So to work out the concentration, I need that number of moles divided by the total volume, which is 25 mils, plus 15 mils, which is 40 mils. Right, so this here, down here, is going to be 0.00375 over 0.04 divided by 0.04 equals, that's going to be 0.09375. Right, so I've got everything I need now. So I'm going to sub my numbers in. I'm going to sub my KB in here. So that is 4.274 times 10 to the negative 6. I'm going to assume that these are the same because they're only coming here from its dissociation of this thing here. It's not a buffer situation. So we've got x squared over, and this number here, 0.09375. So if I rearrange, I'm going to multiply that up, and then I'm going to square root it. So I'll do that now, just off screen, sorry. Times 4.274 times 10 to the negative 6, and square root that. So that gives me 6.329 times 10 to the negative 4 moles per litre of OH minus. Right, so now I've got the concentration of OH minus. I'm going to negative log that, and I'm going to subtract it from 14. So negative log of OH, I'm just going to go 14 minus, like that. So I'm going to go negative log answer equals 14 minus answer equals, and that gives me 10.8 to 3 significant figures. Actually, that was done reasonably well by a reasonable number of you, so great job. And we carry on. We've got a couple more questions to go. So we've got a different titration. And this was quite confusingly written, I guess, because they changed the NaOBr to just OBr minus and the HCl to just H3O plus. And so we presume that we've got some Cl minus and some Na plus ions floating around in solution here. As you know, these are irrelevant, so I'm just going to ignore them. This was quite a tricky question, and only a couple of you really nailed this. So a couple of things. Compare the relative concentrations of this and this. That's the answer. Too many of you did not tell me if that was the same as that, that was bigger than that, or that was smaller than that. That's the crux of the question. And we had to include equations, but you had to include relevant equations, and many of you just wrote that equation 3 times, which is not what we wanted. So at 0 mils, so this is at the first, before we start the titration. So at this point, we only have NaOBr or OBr minus. So it's basically before we've added any acid. So we've got a weak base. And so the equation that we want is the weak base reacting with water. Okay, so that's my equation there. If we've only got a weak base and it's sitting in water, that's the reaction that's happening. So as this is a partial dissociation or partial reaction, the concentration of OBr minus is greater than HOBr, which is so little, we assume it's negligible. But the important bits here is that related to the partial dissociation. Now, many of you actually did that okay, so good job if you did that. And then we got a bit trickier. So the next point is 7.5 mils of H3O plus, which if we look back here is our half equivalence. So lots of you did really well. You said this is half equivalence. Okay, And some of you even learned that the concentration of the weak acid and the weak conjugate base would therefore be equal. But you couldn't quite tell me why. So this one was a bit tricky. So I think what I would have done here is this one I would have used the titration equation. So I'm just copying that from the titration over there. But I needed to use my number of moles here. So if I said I had started with X moles of this, and at half equivalence, I'd added half X moles of that. So what I've got is, at equivalence point here, I've got half X moles of OBR minus, and I've got 0 of this, and I've got half X moles of HOBR. So that's one way you could have kind of shown it. I'd prefer you to write it in words as well. So that would be the H3O plus has half reacted with the OBR minus to leave half the original moles unreacted. That's OBR minus, and form the same number of moles of HOBR. So something like that. So the explanation needed to be there as well. And at 15 mils, this is our equivalence again. Right, this is our equivalence point. So at equivalence, we've got to recognise at equivalence, we've added equal moles of these two, so we've only got products. So I'm just going to write that, equal moles of OBR minus and H3O plus have reacted, leaving only products. And here's where we needed to do our explaining. HOBR is the product, and so therefore if it's sitting in water, it's going to react with water as such. So as this is a partial dissociation, the concentration of HOBR must be greater than the concentration of OBR minus. So it's essentially the same reasoning as this one, but look, it's for a different reaction. This is the weak base and this is the weak acid. So we needed to have those equations in there. That was actually an excellence question. It's a really good one to go through to make sure that you understand what's going on there. And our last two questions are two merits. So this one is, why is methyl red good for the titration in B but not A? So the equivalence point pH in B, if we look at the half point there, is probably about just under 5, whereas we know that the equivalence, oh crikey, sorry, I'm all over the show here. So the equivalence point for B is 5 and the equivalence point for A is 10.8. So let's just transfer this over here. So equivalence point pH for curve A equals 10.8. B equals approximately 4.8 to 5. Okay, so I've said pH here. The indicator changes colour at a pH equal to plus or minus 1 pH unit around the pKa of the indicator. In this case, 4 to 6 pH, 4 to 6. Okay, so in curve B, the pH at equivalence is around 5, so the colour change occurs at the equivalence point volume. And it probably is quite good to put here the volume at the steepest point of the curve. That's probably a good thing to write. Whereas in curve A, the colour change would happen at 0 mils before the titration started, if you have a look at the curve. So if we have a look at that curve back here, let's go back a couple of pages. So we look at pH 5 where it's changing, that's at 0. So actually if you were doing this titration, you wouldn't even get a colour change. You wouldn't even get a volume. It would be that bad. So that's why we wouldn't use that one. This one here is actually a bit redundant because this is again the same kind of idea as here, the equivalence point, and actually the same kind of idea as here. So if you didn't get these very well, you are unlikely to get this one very well. So key point, pH at the equivalence. At equivalence, the number of moles of the acid has equaled the number of moles of the base and the titration. Therefore, there are only products. Okay, so in A, the product from the reaction is, let's go back and have a look. Reaction A, the product is NaOBr, right, or OBr minus. So the product is OBr minus, a weak base. So let's write an equation for that. Always a dissociation equation, eh? Okay, so at that point, at the equivalence point, we're saying, therefore, OH minus ions are formed, and the concentration of OH minus is greater than the concentration of H3O plus. Therefore, the pH is going to be greater than 7. Okay, that's pretty much all you need, right? And then for graph B, the product, and that one is HOBr, which is a weak acid. Write our equation. And in this one, we say H3O plus ions are formed. Therefore, H3O plus conc is greater than OH minus conc. Therefore, the pH is less than 7. So you could probably elaborate a little bit more on that, but you definitely need those equations, and really important to nail what's happening at that equivalence point. And that is the end of the exam walkthroughs. And obviously we'll be going on to this question in class next week. Haere rā team, have a great day.